Hey everyone, and welcome to this deep dive where we're going like microscopic today.
Oh, yeah.
We're diving into the kinetic model of matter,
Very
and
cool.
we've got some super interesting educational resources from Open Educational Resources slash Open Source Physics at Singapore
Okay.
to kind of unpack all this with us. And the coolest part is after the deep dive, we'll give you guys links to some really awesome interactive simulations and games so you can see all this stuff we're talking about in action.
Yeah, that'll be fun.
But okay, just to start off, think about this for a second. Even solid objects,
Mm.
the things we touch every day that feel totally still, they're actually like buzzing with molecular activity constantly.
It's true.
It's pretty wild.
It's pretty wild. The kinetic model of matter helps us understand that all those states of matter we know so well, solids, liquids, and gases.
Right.
It's all about how the molecules are arranged and how much they're moving.
Okay, so like we learned in grade school, solids hold their shape, liquids flow, and gases fill up whatever container they're in. But what's actually going on to the molecules that make them act so different?
Yeah, so it all comes down to the forces between the molecules and the energy that those molecules have.
Okay.
So in a solid, the molecules are really tightly packed together and they're super attracted to each other, like they just want to be close. They
Right.
can vibrate in place, but they don't have enough energy to actually break free from their little spots.
So like if you imagine like a super crowded room and everyone's just kind of like jostling each other,
Yeah.
but no one can really move anywhere.
Yeah, exactly. That's a great analogy.
Okay.
Now, in a liquid, the molecules, they have a bit more energy so they can move around a little more, slide past each other, which is why liquids can flow.
Right.
But they're still pretty close together and they're still attracted to each other, which is why they keep a specific volume.
Okay, so then a gas, that's where the molecules are like having a rave.
Yeah, basically. In a gas, the molecules, they've got so much energy that they just overcome the forces holding them together. They're free to zip around randomly and they're bouncing off each other, bouncing off the walls of their container.
So that's what's making the pressure, right?
Yeah, exactly. All that bombardment, that's what creates the pressure.
Oh, that makes sense.
Yeah.
Okay, so we talked about pressure now.
Yeah.
Where does heat fit into all this? It's not just how hot or cold something feels to us, right?
You got it, me. Heat is actually energy that's moving.
Okay.
It's energy in transit. So when heat flows from something hotter to something colder, it's transferring that thermal energy.
Okay.
And that energy, it directly impacts how much the molecules are moving.
So the more heat there is, the more those molecules are just going crazy.
Exactly. You
Yeah.
got it. The more heat energy there is, the faster the molecules are zipping around. And that affects stuff like the pressure and even what state of matter something's in.
Oh, right.
Mm.
So like think about when you heat up an ice cube,
Yeah.
it melts into water,
Yeah.
and then if you keep heating it up, it boils and becomes steam.
Exactly. And all of that is happening because you're giving those molecules enough energy to like bust out of their rigid structure in the solid and then even further apart in the liquid to become a gas.
That makes sense.
Yeah.
But there are some things people get wrong about heat. Like I've even heard people say that heat is like a substance that flows into things.
Yeah, that's a really common one, but it's not quite right. Heat is the transfer of energy, like we were saying. It's not a substance itself.
Right.
Think about it like this, like when you push a swing, you're giving it energy to move. You're not transferring push as like a substance.
Oh, that's a good analogy.
Yeah.
That clears it up.
Yeah.
Okay, what about the idea that molecules are just randomly wandering around? I thought they moved with like a purpose, in a straight line until they hit something.
You're on the right track.
Yeah.
So molecules do move in straight lines, but only until they bump into something else.
Right.
Whether it's another molecule or the wall of the container, it's kind of like a constant game of molecular billiards going on. Each collision makes them change direction, but they're still moving with all that energy.
So it's like chaos, but there are rules.
Yeah, you could say that.
Hmm.
It's organized chaos, and it's this organized chaos that's behind so many things we see in the world.
It's amazing to think that these tiny little molecules just bouncing around has such a huge impact on everything.
It really is. And speaking of seeing that impact, the Open Educational Resources slash Open Source Physics at Singapore website has these amazing simulations
Oh, yeah.
that can help you actually see what we've been talking about.
Yeah, those simulations are really cool. I remember one that shows you how molecules act in different states of matter.
Uh-huh.
You can actually see how different they're moving and how much space there is between them when it's a solid versus a liquid versus a gas. It's way easier to understand than just trying to picture it in your head.
Oh, for sure. And they've got ones that show you what happens when you add heat energy to something. You can watch the molecules start moving faster, bumping into each other more often, and even switching between those states of matter. It really brings the kinetic model to life.
Oh, I'm definitely checking those out later. It makes you wonder what would happen if you just kept taking away heat, like forever. Would the molecules ever just completely stop moving?
That's a great question, and it actually leads us to something super interesting called absolute zero.
Okay, let's talk about that. What is absolute zero, and can we ever actually reach it?
So absolute zero, it's the theoretical temperature where like all molecular motion would just stop.
Hmm.
It's negative 273.15 degrees Celsius or 0 Kelvin.
Wow, that is cold.
Okay.
So, but we've never actually gotten to absolute zero, right?
Right, it's more of a theoretical limit.
Okay.
You know, the laws of thermodynamics, they suggest that it's actually impossible to get to absolute zero
Mhm.
because you'd have to remove like an infinite amount of heat energy from a system.
So it's kind of like this horizon you can keep chasing but never actually reach.
Exactly. Scientists have gotten super close, though, like billionths of a degree above absolute zero.
Wow.
But getting to actual absolute zero, it's still this like elusive goal.
It's wild to think about what a world would even be like, where like everything is completely still at the molecular level.
Yeah, it would definitely be a very different world from what we know.
Yeah.
But even though we can't actually get to absolute zero, thinking about it, it helps us understand a lot about heat and energy.
Right. It kind of shows us that like everything's in motion, at least a little bit at the molecular level.
Yeah.
And speaking of motion, I remember those simulations showed how molecules are constantly hitting each other. What's up with those collisions?
Oh, yeah, collisions are key to understanding things like pressure and diffusion.
Yeah.
You know, pressure is the force that gas molecules put on the walls of their container when they're constantly bumping into them.
Right. So more collisions means higher pressure.
Exactly. If you heat up a gas, the molecules move faster, they bump into things more often, and boom, higher pressure.
Which is why a sealed container can explode if it gets too hot.
Exactly. The pressure inside just gets too intense.
Wow. Okay, that makes sense.
Mhm.
So what about diffusion? How do collisions explain that?
Okay, so diffusion is how molecules spread out, you know, from where there's a lot of them to where there's fewer of them.
Right.
And it's all driven by those random collisions we've been talking about.
So imagine like I spray some perfume in the corner of a room.
Yeah.
How do those perfume molecules end up all over the place?
So at first, all those perfume molecules, they're all hanging out in that one corner. But they're constantly bumping into each other and into the air molecules, which makes them change direction all the time.
Uh-huh.
And over time, all those random bumps make the perfume molecules spread out until they're like evenly distributed throughout the whole room.
So even though each molecule is moving randomly, the end result is that they move from high concentration to low concentration.
Exactly. And it's all thanks to those collisions.
That's cool. Now, I remember those simulations showed that heat can actually change how fast diffusion happens. Why is that?
Well, remember when you add heat to something, the molecules start moving faster.
Right.
And moving faster means more collisions, and that means faster spreading.
So if I want my perfume to spread faster, I should just crank up the heat.
Well, you might end up pretty sweaty in that room, but yeah, in theory, that would speed up diffusion.
Good point.
Mm.
Okay, so we've seen how collisions explain pressure and diffusion. What other things can we understand with the kinetic model?
The kinetic model is really awesome for understanding those changes in the state of matter. You know, we talked about how adding heat can make a solid melt into a liquid and a liquid vaporize into a gas.
Right. But what's happening with the molecules during those transitions?
Okay, so in a solid, the molecules are all stuck together in that fixed structure because of those strong intermolecular forces.
Okay.
When you add heat, the molecules soak up that energy and they start vibrating faster.
It's like they get all riled up and ready to break free.
Exactly. And as you keep adding heat, they eventually hit that point where they've got enough energy to overcome those forces holding them together, and they can start moving more freely.
And that's when melting happens.
Exactly.
Yeah.
The solid turns into a liquid.
So they busted out of their rigid structure, but they're still kind of hanging out close together.
Right. In a liquid, the molecules are still close and they're still attracted to each other, but they're not stuck in those specific spots anymore. They can move around and slide past each other, which is why liquids flow.
And if you just keep adding more and more heat, they eventually get enough energy to break free completely and become a gas.
Exactly. In a gas, the molecules, they're far apart, moving all over the place and basically independent of each other.
It's incredible that these simple ideas of molecular motion and attraction can explain so much.
Mhm.
It's like we figured out a secret code to how matter works.
Yeah, it's a really powerful model.
Yeah.
And those interactive simulations we mentioned earlier, they're a fantastic way to see all this in action. You can mess around with things like temperature and pressure and see how those changes affect molecules in different states. It's a
Yeah.
lot more engaging than just reading about it.
I am definitely spending some quality time with those simulations after this deep dive.
Oh.
Okay, welcome back. So as we're wrapping up our deep dive into the kinetic model of matter,
Hmm.
I'm just thinking about how much this model can explain.
Yeah, it's pretty remarkable.
It seems so simple, but we've covered so much, from how solids, liquids, and gases work to that crazy concept of absolute zero.
And we've seen how it all plays out in the real world too, right? Like in things like the pressure in your car tires or how bridges expand and contract.
Yeah, those real-world examples are what really make it click for me. It's not just some theory, it's like actually affects how we build things and how we interact with the world around us.
Absolutely. Knowing how matter behaves at the molecular level, it's crucial for all sorts of fields like engineering, material science, even medicine.
Right. And speaking of those interactive simulations from Open Educational Resources / open source physics at Singapore, they've been so helpful for understanding all this stuff.
Oh, for sure. Visualizing these concepts is like the key to really getting it. And those simulations let you play around with different variables and see what happens. It's way more fun than just reading about it in a textbook.
Yeah, for real.
Hmm.
One simulation that really stuck with me was the one that showed how a solid melts into a liquid when you add heat.
Yeah.
You can actually see those molecules vibrating faster and faster until they just break free from their spots.
It's such a great way to see how that energy transfer at the molecular level causes those changes in the state of matter. And it shows you how important those intermolecular forces are in determining how different substances behave.
Before this deep dive, I kind of just took the world for granted. Like I knew that ice melted and water boiled, but I never really thought about what was happening with the molecules.
Mm. Yeah, it's easy to not think about that hidden world of molecules, but once you start to understand those principles, it's like a whole new level of understanding and just awe.
Yeah, it really is. Now, when I see something melting or boiling, I'll picture those molecules just buzzing around, getting more and more energetic and breaking free. It's like having a secret window into this invisible world.
Exactly. And that's the beauty of the kinetic model. It gives us this framework for understanding how matter behaves, from the tiniest atom to like the biggest planet.
It reminds us that even the most ordinary things can be fascinating if we just look a little closer.
Absolutely.
And it shows us how powerful science is for revealing the hidden mechanisms that run the universe.
Well said. So, as we wrap up this deep dive, I encourage you to keep exploring this world of molecules in motion. And remember, we'll be sending you those links to the interactive simulations so you can keep experimenting and learning.
Awesome. Thanks for joining us on this journey into the fascinating world of matter. We hope you've gained a new appreciation for those invisible forces that shape our everyday lives.
Yeah, it's been fun.
Yeah. Until next time, stay curious.